Hey guys, so in this video we're going to quickly look at how polar coordinates correspond to Cartesian or rectangular coordinates. So we're going to jump right in. I'm going to take a gander here at the rectangular coordinate system, which if you don't remember is really just that traditional XY axis that you see, where if I have a particular point that I want to represent in this system, like the point, let's say -3, 3, this is written as a combination of the direction in the x and the direction in the y, according to positive to the right and positive up. So if I were to plot this point in here, I'd go 3 to the left and 3 up, and that would place me at this coordinate right here. Okay, so now the polar system, rather than having a left, right, up, down direction, uses a distance from the pole and an angle at which that distance is directed. Okay, so what that looks like is this. So the pole corresponds to, in this Cartesian system, the origin. So the origin is the same as the pole in polar coordinates. The polar axis is the same as the positive x-axis, the place that we would normally measure angles from when sketching angles in standard position. And rather than a combination of x and y, a polar coordinate is determined by a radial distance and an angle. So to get to this same point in polar coordinates, I would measure a radius, r, to that point. In this case, that radius is going to be 3 rad 2, and an angle from this polar axis to where that radial distance forms the terminal side. In this particular instance, that's going to be 135 degrees. So the point -3, 3 in rectangular coordinates is the same as 3 root 2, 135 degrees in polar coordinates. Now you could also represent this angle instead of 135 degrees. You could represent it in radians. It'd be 3 pi over 4. So another way of writing the same thing in polar coordinates would be 3 root 2, 3 pi over 4. So essentially it's just an angle and a distance rather than two directed distances. And because these coordinates represent the same thing, there's a way to convert from one to the other, of course. So if I'm looking to convert from polar to rectangular, I'm just going to write on my grid here a couple of things so that I can easily see how the two combinations relate. So I need to get from a given polar coordinate, r and theta, to its corresponding rectangular coordinate. Well, if it's given as r and theta, those are given parameters. So I know that the radial distance is r, and theta is the angle formed between that polar axis and that radial distance. So I'm just going to draw in a couple of other things. So this should be equivalent to some xy coordinate in the Cartesian system. So I'm going to draw a height to represent the y value and a directed horizontal distance to represent the x value, because that's how we would get x over and y up would get me to the same thing if I'm measuring in Cartesian coordinates. So then we can use some trigonometry to relate these values. So first off, if r and theta are given to me, and I want to find y, well, the trigonometry tells me that if I were to take sine of theta, I would get the opposite over the hypotenuse, which would be y over r in this case. And if I solve that for y, I get that y is equal to r sine theta. So that's essentially the formula for the y coordinate. Take the radial distance times sine of the given angle. And for the x value, it's going to wind up being cosine, would give me x over r, which will tell me that x is r times cosine of theta. You could also arrive at these, instead of using right triangle trig definitions, you could use the unit circle trig definition and then just solve for x. That's essentially where they come from. Okay, so those are those two formulas. We may also be interested in converting from a rectangular coordinate to a polar coordinate. So I'm just going to scroll down. And in that case, I'm just going to do a little bit more math to relate these the other way. So say in this instance, I'm given x and y, and I want to get the r and the theta. Well, because this is a right triangle, because the x and y axes are perpendicular, I could use the Pythagorean theorem to get that r squared would equal x squared plus y squared. And if I root each side, I would get that r is the square root of the sum of the squares of x and y. Okay. Technically, it could be positive or negative, but I'm just going to write it as the positive version because we could just as easily take a different angle to get the negative. Okay. Now to find the angle, I'm going to again use trig, but since x and y will be the givens, I'm going to use the tangent ratio. So I know tan of theta would be opposite over hypotenuse, which tells me that theta, if I apply inverses, is whatever the inverse tangent of y over x is. And that's the formula for theta. It's whatever tan inverse of the ratio y over x is. Okay. And that's it. That's essentially the conversion. So if we look at a couple of examples, applications of these formulas, here I'm going to convert a polar coordinate into a rectangular coordinate. This is, again, my conversion formulas that we just derived. So if I look at the first example, I know that r is 2, and I know that theta is 5 pi over 3. So the x coordinate would be 2 cosine of 5 pi over 3. Now, cosine of 5 pi over 3, this is a reference angle, 5 pi, I wrote 5 pi over 6, so this would be 5 pi over 3. It's a reference angle of pi over 3, and I am in the fourth quadrant. So cosine is going to be a positive value. Cosine of 60 is a half, so this will be 2 times 1/2, which will give me 1. And then the y value, I'll do the same thing, only now it will be sine of 5 pi over 3. So that'll be 2, again, in the fourth quadrant, sine is negative, and sine of 60 is rad 3 over 2. So this will give me negative root 3. So the xy coordinate would be 1, negative root 3 for that value. Why don't you take a moment, pause this video, see if you can apply that same reasoning to question 2, and then I'll reveal the solution for you. Okay, so hopefully you've had a chance to take a look. Here is the solution to that question, going again through the same formulaic approach, and I'd arrive at these values. So now I'm going to take a look at converting the other way. If I want to convert a pair of rectangular coordinates into polar coordinates, so given an x and y value, again, the formulas for those, as we mentioned, are here. Here I've written it as tan theta equals y over x, but you could just as easily write it using the inverse. I just find it easier to remember this way. So this is my x value. This is my y value. I'm just going to plug them in, and I'm going to get r is the square root of x squared, which would be 4, plus this would be the product of 4 times 3, or 12. 12 plus 4 is 16. So then I get r is 4. Tan of theta is equal to the y value, 2 root 3, over the x value 2, which gives me root 3. And then I'm just going to think, I know offhand that's one of the special angles, so that tells me that theta, if I'm doing this in radians, is going to be, well, in degrees, that would be 60 degrees, so in radians, that'd be pi over 3. So that gives me the coordinates r theta. R is 4, theta is pi over 3. Now, technically, you could also write this in another way. You could write this using the negative version, negative 4, and you would just use the angle directed opposite of pi over 3, which would give me 4 pi over 3. Okay, so it's technically, there's 2 solutions to it, but this is perfectly accurate. Okay, dokes. So why don't you take a second and pause this video, try number 8, and then I will reveal the solution to that one as well. All right, so once we do number 8, using the same formula conversions again, I have it here. So this is the value I would get. So I could use, again, either one of 2 solutions. I can use the positive radial distance and 7 pi over 4, or I could use the negative radial distance and I get 3 pi over 4. Doesn't really matter. It's just talking about which direction we're headed. Okay, so hopefully that was helpful for you for clarifying the difference between the 2, and then I'll see you in a future video.